Good morning, good afternoon, and good evening to everybody wherever and whenever this podcast finds you. Welcome to the Did You Know podcast. I am your host, Dustin. Today I am going to be talking to astrophysicist Ethan Siegel. It's a very in-depth conversation, and it's part of my rebranding to kind of cover a variety of topics that relate to the kind of ever-changing aspects of our world and kind of this fulcrum of history, as well as just things that I find really interesting. And this falls into kind of both categories as we discover more and more things about our universe. And this topic is just extremely interesting to me, and I was really thankful that Ethan was able to make time to talk to us. Before we get into the show, if we could just cover a few things. One, I'd like to thank our sponsor, eToro, a smart trading platform. They do over $1 trillion in trading annually, where they trade Bitcoin and other traditional assets. They have over 11 million other traders in their social network platform there, and some really innovative tools that help you become a better trader, a smarter trader, and be able to be secure. So if you could also head over to iTunes and leave a review, 5 stars, if you think that I'm worth it, I'd really appreciate it. That helps the podcast the most. Also, head over to supportmypodcast.com, where you can find all the other ways to support the podcast, but also there's a little button there. It says listener discounts. That's absolutely free for all my listeners. That's you right now. And if you go over there, click that button, you'll see a bunch of different discounts from Trezor and KeepKey hardware wallets for holding Bitcoin and other crypto assets, to Bitcoin.tax, which helps out your tax accounting at the end of the year, Mushroom Coffee, and a lot of other stuff. I am continually updating this, and I'm working on getting more and more different discounts for you guys. So head on over there. And most of all, I'd like to thank you, the listener. I mean, you guys make all of this possible, and the numbers have been doing very well. I'm actually very happy with it. So please share it, and also, follow us on social media. You can find all those links at didyouknowcrypto.com/platforms, or just go to didyouknowcrypto.com and it'll all be there. And once again, thanks for listening, and enjoy the show. Today I welcome Professor Ethan Siegel, an astrophysicist, former professor at Lewis and Clark College, Forbes contributor, and science writer. He has written the books Beyond the Galaxy, How Humanity Looked Beyond Our Milky Way and Discovered the Entire Universe, and The Science of Star Trek. His blog, Starts with a Bang, has won numerous awards and covers topics from black holes to the ideas of time travel in a way. Welcome to the show.
Thank you, Dustin. It's my pleasure to be here. I'm really excited to be here and to share what we know and how we know it with you and all your listeners.
It's as I kind of said earlier before we started recording, I'm really excited to have you on. And as I explained as well, I kind of apologize in advance that a lot of these questions may seem, kind of very basic and have already been talked about a lot. But I think the spreading of knowledge kind of requires this monotonous repetition for them to kind of move from the niche kind of to the mainstream. But first, I'd love to hear about you, and specifically if there was any, moment or kind of evolution of events that, set you on this path to find out, to find your passion that's, seeking the truths of the universe.
Well, everyone has their own story, and I don't think mine is unique, but I'm happy to share it with you. And I do want to say, I think one of the big keys for anyone who becomes an expert in anything and wants to share it with the world is not to think of it like, oh, I'm going to have to teach the same thing over and over again to every new person I talk to. That's not really what any of this is about. This is about remembering what it was like to wonder about a question that you didn't know the answer to, and then to remember what it was like when you discovered that answer for yourself and it made sense to you. So when I talk about things that happen in the universe or things that I've come to learn about the universe, these are not things where I just looked it up on Wikipedia or something like that. This is something where, I think it's important to remember, what is the context like? What is your mental thought like? What do people think when they conceive of something? And then how can we make sense out of it based on what you know, without going too far out of your comfort zone? So I know a lot of people, when they think about physics or astronomy or astrophysics, they're like, "Oh, that's really hard, and how would I ever learn something like that?" And for me, I guess I'm lucky. I'm someone that math and science were two of my strong points when I was young. But I was interested in a lot of different things. There's that old saying about, just because you're hung like a moose doesn't mean you got to do porn. And I think that's true in all walks of life. Like, just because you're good at something doesn't mean that's the thing you have to pursue. I like to think that you're going to be successful pursuing something where your talents and your interest both overlap. So for me, when I graduated from college, I had three different majors because I wasn't sure what it was I wanted to do. And after I graduated, my job was, I went out and I got a job teaching public school. And it was while I was doing that that I would say I had my first major crisis as an adult, because I was working at this job I had gotten after college, and I didn't love it, and I didn't know what I wanted to do next, but I knew it wasn't to keep doing what I was doing. And I think we use the word crisis when we talk to one another like it's some sort of a dirty word, like it's, oh, like only weak people have a crisis, or only people who don't have it figured out have this problem. I don't think about it that way. I think about it as, whenever you're doing anything, you have to continually be asking yourself, am I on the right path for me? And if that answer is no, if that answer is, I don't enjoy the things I'm doing, I don't think the thing I'm working towards is worth it, you owe it to yourself to ask yourself, what is it you'd rather be doing? What is it you'd rather be working on, spending your time doing, spending your effort on? Um, and when you figure that out, go for it. And so for me, I started asking questions like, well, if I could learn any one thing at all, what would it be? And I thought, like, well, like, let's go for real. What are the real things I want to learn? I want to know what this universe is. I want to know what it's made out of. I want to know how it got to be the way that it is, how it was born, how it grew up, and how it will end. And I was like, oh, that's all? But I was like, no, I really want to know these things. I want to know the best answer that humanity, in our scientific knowledge and in the entire endeavor of civilization, um, what are the best answers we can give for that? And with what confidence can we state it? And I learned while I was asking these questions, actually, this is not a question for theologians or poets or philosophers like it was for thousands of years. But over the last couple of centuries, this has fallen into the realm of science. And these questions that have puzzled our ancestors for all of existence, we now have robust, definitive answers to. And I wanted to be part of it. The fact that this was something we could learn made this something for me that I felt I had to learn. So that really spurred on my decision to become a professional at this, to find a graduate school that would teach me all about this, where I could find an advisor that I'd be happy learning all of this from, and where I could find a place where I was happy with the overall strength of the department and the overall education quality I'd get, and where I could also stomach living for, for most people, it's 4 to 7 years. And for me, it wound up being about 5 1/3 was how long it took me to get my PhD. But once I started down that path, I never wanted to look back. And I knew there would be more crises in front of me as I navigated, what do you want to do and what kind of job do you want to have? And do you want to be a professor, or do you want to be a writer, or do you want to be a communicator? And what are all the things you can do? Crisis isn't a dirty word, but sticking with something just because of inertia, just because you have been doing it and you can do it, I think that's the recipe for having a life that people expect you to have that you don't actually want. So when you find that thing for yourself where your passion and your talents overlap, I don't think there should be anything that you should let hold you back if that's what you want to do.
Well, you mentioned this idea of that there's answers to questions that we've pondered over, and I think that people like myself who are kind of just mere topical observers of the pun intended, the universe that you live in, are captivated by the space and what's out there, which kind of reflects in the entertainment that we consume, Star Wars, Star Trek, Interstellar, etc. And I think this is kind of a branch of Arthur C. Clarke's third law, which is any sufficiently advanced technology is indistinguishable from magic. And for many, our inability to kind of interact physically, tactily with these the theories and the facts about our universe that you talk about kind of makes for a lot of people this kind of basically indistinguishable from magic in a way. And I think because earlier in time, we didn't know how disease worked or what was beyond that mountain range. It allowed our imaginations to run wild. And the only place that in modern times you can really kind of do that is still in space, in physics. And so to many people in the world, uh, people like yourself are kind of akin to these kind of ancient shamanistic diviners of unknown knowledge. And has that been kind of your experience? And if so, why do you think that is? What is it about the human experience that finds so much the unknown kind of creates these kinds of views of people like yourself who do hold that knowledge?
Of course, I don't think of myself that way because when I start thinking about the universe, I think about all the remarkable things we do know and what our different ideas about it were and what the data in all these different regimes says and how to synthesize all of that together to come up with the best coherent picture that we can and to think about it in terms of, okay, what are the uncertainties and where are the frontiers and what don't we know and what should we be looking at if we want to find out the answers to that. These to me are the same logical questions that you would ask if you were saying like, oh, I'm holding a soda can in my hand, what's it made of? And you would think, oh, well, there's a way I could go about it to figure out what it's made of, right? Like I can put it on a scale and I can put it in a graduated cylinder and I can measure its mass and its volume and I can figure out its density and I can try and figure out what else has that same density that it might be made of. Or I could talk about it as, oh, well, it's made up of things and I can cut them smaller and smaller and smaller until I can't cut them anymore. And then I can see what are these atoms made out of, or what are the particles that made up these atoms? What are those? And I could ask it that way. Like these are questions you can ask about anything. For me, I feel like the only reason people look at me as like, oh, like he must be like some kind of shaman or a numerologist or a mathematician or something like that. And I think the only reason people think that sort of way is either because they think about math and physics and space and all of that and they're intimidated by it and they think of it as something that is so far outside of their everyday experience that you'd have to be a genius rather than someone who has a talent at something, who works hard to develop it. It's easy to make that leap. But I think the other reason is that so much of what underlies this, and I'm talking about relativity and quantum physics, these are concepts and really entire fields that it's very difficult to develop an intuition about because they're so thoroughly divorced from our day-to-day experience. We have the experience that if I'm on a car going 60 miles an hour and I take a baseball and I throw that baseball out the window at 60 miles an hour, then I need to add the 60 that the car's moving to the 60 that the ball's moving, and I'll get 120 miles an hour is the speed that I throw my ball at. Unfortunately, in relativity, that isn't how things work. In relativity, when you get close to the speed of light, you can't just add your velocities together. You have to do this special mathematical trick called a relativistic transformation in order to figure that out. In quantum physics, normally you'll say like, oh, we could just measure where is this particle and I'll have its position. But in quantum physics, even a quantity like position, asking where is this particle, it has this inherent quantum uncertainty to it. It's not described as a particle. It can only be described in terms of a wave function. I think those two aspects, the fact that people know, okay, quantum physics is different than my experience, relativity is different than my experience, everything that happens in space relies on one or both of those. So, wow, like you must be real smart to know something that is very foreign to me. And you know, I'm not going to pretend like I think I'm stupid, but I'm also not going to pretend like I think you're stupid or any of your listeners are stupid. The reason that this has started to make sense to me is because I spent years working on it. I think people who are just peripherally familiar with pop culture would say like, "Oh, wasn't there something about how you need to spend 10 years or invest 10,000 hours in something to become an expert at it?" And I would say maybe that's right, because if you look at me and when I started my undergrad career when I was 18 and when I finished graduate school, which happened when I was 28, that was probably about 10 years. And even if you take out the year that I taught and the times where I wasn't working, like I probably put in a good 10,000 hours. But it was really only at about that point, right when I was on the cusp of getting my PhD, that I actually felt like I reached that milestone. There are, I think, three steps that everyone goes through when they try to become a real bona fide expert at something. The first step happens when you're young and you don't even know what it is you don't know. And you have this like, oh, I either know everything already or I'll learn all the things I need to know in short order and this will be fine. And then you get that rude awakening where you sort of think to yourself, oh no, oh, I don't know anything. It's abominable how I don't know what I'm doing, and people are going to find out that I'm a fraud and I'm an imposter, and I don't know what I'm doing. And then by the time you're ready to graduate with your PhD, you've come to this realization where you're like, actually, my advisor doesn't know what they're doing any better than I know what I'm doing. And my colleagues in my field, they don't know what they're doing any better than what I'm doing. In other words, it's not that I think I know more, even though, like, clearly I have learned things. It's that I'm realizing what humanity doesn't know, that I'm starting to realize what nobody knows, where those frontiers are, and what all that means. So the joke is that you think, I know everything, and then you think, I don't know anything, but then it's okay because you realize neither does anyone else. And I think once you get to that third phase where you recognize that nobody knows the answers to these questions that you're asking, that you start to be comfortable with that you start to be comfortable with, yeah, nobody knows everything. The amount of information in the universe is limited. The amount of time that humans have been around doing science is limited. So therefore, what we're going to know is also going to be finite and limited. We know a tremendous amount, and I don't want to belittle that, because that's what I get real excited about, is what we do actually know and how we know it and who can I share that with. But I also don't want to pretend like this is totally inaccessible to anyone. Immunology appears totally inaccessible, but you can become an immunologist. Well, cosmology and astrophysics feels inaccessible to a lot of people. But not only can you do that, but for the first time this year, a cosmologist was awarded the Nobel Prize in Physics for fundamental work in theoretical cosmology.
Well, I think that's very well put, because I just with anything, whether people are just talking about whether it's coding or marketing or just anything in life, a lot of that people have maybe a basic understanding of it, but without a putting in those hours, it does, anything seems quite alien to your own experience. But you actually have an upcoming book, correct?
I do. I do. I have a third book that I have a first draft written on, and it is about the origin of the universe. It is about what happened before the Big Bang. And I know you're all probably listening and saying, what do you mean before the Big Bang? Isn't the Big Bang the birth of space and time? And I understand that that is what most people think. And I think that's one of the biggest misconceptions about the universe. And my next book is going to be about how we figured out what our cosmic origins really are and where the Big Bang came from.
Yeah, because I'd heard you talking about this, and it kind of blew me away because, you know, I think that myself, like you said, it's one of the biggest misconceptions, and everyone's only got so much bandwidth, right? But my understanding, basically, up until a few weeks ago, was, I guess, something that's already 40 years out of date. That it didn't really start with that because there's another, I guess, if you want to call it, a level to it, and I think that helps explain a question that I have or had, I guess, which was, when people go, well, the universe is expanding, and then they go, into what? Right. And, maybe if we could step back a bit, kind of go over the Big Bang kind of as just kind of an overview of it, what happened, but also, cosmic inflation, and what is that? What was before the Big Bang, and kind of how did all this get started?
Well, so let me start off with with the facts that led us to discover something way before the Big Bang to lead us to discover the expanding universe. It's really hard to fathom, but 100 years ago, people did not know what the universe was. And that seems like a silly thing to say, but think about it this way. All the stars we see in the night sky belong to the Milky Way galaxy. There are only a few objects that you can see with the naked eye today that are outside of our own galaxy. In fact, when I say there's a few, there are like four. There's the Andromeda Galaxy, there's the Triangulum Galaxy, and there are the Large and Small Magellanic Clouds, which I can't see because I am at too far of a northern latitude to see it. But I can see Andromeda when it's dark enough. I can see the Andromeda Galaxy where I am. And you can too with your naked eye. You could see these four galaxies. You could see up to four other galaxies dependent on where you are. But we did not know 100 years ago that those objects we were seeing were indeed galaxies unto themselves, that they were objects outside of the Milky Way. We didn't know that. The only way we found out was by combining two observations and one theoretical fact. The first observation was that when you measure the stars, you can measure how fast they're moving relative to you, if they're moving towards you, if they're moving away from you. Have you ever heard like the ice cream truck go by in a city and notice that when it comes up on you, the song that it's playing is higher pitched, and when it's moving away from you, the song it's playing is lower pitched? Or if you're not an ice cream fan for some reason, maybe you've noticed when like a police siren or an emergency vehicle has done this. If you hear that shift in pitch when something moves towards you versus away from you, that's called a Doppler shift, and that's you hearing it for sound waves. Well, light waves do it too. If a star is moving towards you, its light is going to be shifted towards bluer wavelengths. And if it's moving away from you, it's going to be shifted towards redder wavelengths. All the stars in our galaxy, relative to us, move typically at tens of kilometers a second. The largest ones, the fastest ones, will move at hundreds of kilometers a second. Well, when we started observing these, they called them back in the day spiral nebulae, because they didn't know they were spiral galaxies. They just called them nebulae as a generic term. When you started watching these, you found that they moved at hundreds or even thousands of kilometers a second. And almost all of them, with a few exceptions, and all the exceptions are extremely close to us, they're almost all moving away from us. They're almost all red shifted instead of blue shifted. So that was one fact. But then another fact came in, which is we were able to identify individual stars in these nebulae. And if you know how bright a star is intrinsically, because you know something about astronomy, and then you measure how bright that star appears, you can calculate what its distance is from you. And when you did this for stars in the Milky Way, you'd get distances that were a few light years, tens of light years, hundreds of light years. The most distant stars in our galaxy were thousands of light years away. But when they started looking at stars in other galaxies or in these spirals that they didn't know what they were, the closest ones were hundreds of thousands of light years away, and many of them were millions or tens of millions of light years away. And that was just at the very beginning. So people first off said, oh man, when these observations came in, these spirals are not within the Milky Way. They are their own galaxies. The original term for them was island universes. But the other property of them is they're all moving away from us on average. In fact, the farther away a galaxy is, the faster it appears to move away from us. So why could this be? You know, you might think of like a grenade exploding and shrapnel coming out of it, right? And all the galaxies are like shrapnel. Well, if that was the case, you would expect to see that the farther away you looked, you got fewer and fewer galaxies, that most of them would be close to the explosion and only the most far-flung ones would be farther. But that's not what we see. We see instead, as we look to greater distances, there are greater numbers and greater densities of galaxies. And we see those galaxies are smaller and bluer and lower in mass and have younger stars in them. So when we put this together in the context of general relativity, I like to imagine that I'm a baker. And I'm not baking raisin bread, although that's going to be my analogy. I'm baking the universe. So what I do is I take a ball of universe dough. We can treat it like this is the fabric of space, and I can put a bunch of raisins in it. And I can imagine that each of these raisins is like a galaxy. Now, I'm going to imagine I'm on the International Space Station and I'm in a zero gravity environment and I'm weightless. So this ball of dough sits in my oven in space and it's weightless. And what happens? Well, the oven turns on and the dough starts to rise and cook and the dough expands. What about the raisins? Imagine that the dough is invisible and all you can see are the raisins. If you were on one of these raisins, what would you see? You'd see the raisins that are closest to yours would appear to be moving away, but slowly, because they're close and the amount of dough that there is to expand between you and them is small. But the raisins that are farther away, there's a lot of dough between you and them. And so you can get a lot more expansion, which means by time a light signal arrives from that raisin to you, it's been stretched by the expansion of space. So this is the origin of how we arrived at the idea that, oh, what's happening here? Galaxies are moving away from each other because the fabric of space is expanding. And as time goes on, they get farther and farther away. The universe gets sparser. And also because we talked about radiation and light and its wavelength, we should all be aware that longer wavelength light that's more stretched, is lower in temperature and colder, but light that's hotter in temperature and shorter in wavelength is hotter, right? It's more energetic. So if we are saying, well, what's the universe doing today? It's expanding and it's cooling and it's gravitating, so it's getting clumpier. That means in the past, it had to be hotter and denser and more uniform. And that's what we should see as we look farther and farther away, is we should see that we're looking back in time. We expect, as we look to earlier times and greater distances, we'll find galaxies that are smaller and younger and have merged less. And we do see that. And we should see that the cosmic web, which has grown up because of gravity, gets more and more sparse and more uniform in the past. And it does. And we should also see, if you look all the way back, there should be a time where things were so uniform that you couldn't have formed galaxies and you couldn't have formed stars, and all you had were neutral atoms. And before that, you would even have just the leftover radiation from the Big Bang. And before you see that, you should have had things be hot and dense enough that you could have had nuclear reactions occurring with the very first atoms that the universe formed. So you add all of these things together and you get these predictions that there should be this leftover glow of radiation just a few degrees above absolute zero. That's the leftover glow from the Big Bang. And you should see the growth of this cosmic web in a very particular fashion, dependent on how much matter and dark energy and radiation and neutrinos and all those ratios are present in your universe. And you should be able to say, okay, before we formed any stars, what should the ratios of hydrogen and helium and all their isotopes and all the other elements be? And you do these calculations, and lo and behold, what you theoretically predict and what you observe, they match up super well. That's the origin of the Big Bang. The Big Bang is this idea that the universe is the way it is now because it was hotter and denser in the past and has expanded and cooled and gravitated over billions of years. We now know over 13.8 billion years to give us the universe we have today. So that's the original framework of the Big Bang. But I know what you're saying. You're saying, hey, I don't like to stop where our observations stop. I want to go all the way. I want to go all the way back to not just hot, but infinitely hot, not just dense, but infinitely dense. I want to go all the way back arbitrarily far to the maximum density to a time t equals 0. This is how I want to do it. That's what I'm going to define as the Big Bang. The Big Bang is where you extrapolate everything back so extremely that all the laws of physics break down. You get something like a singularity, which people jokingly say is where God divided by 0, and that's the Big Bang. And to be fair, that was the original idea of the Big Bang. As it was first being explored in the 40s and 50s, that's what people had to say about it. So how do you feel about that? How does that jibe with your mental picture of what the Big Bang is and what the expanding universe is?
Well, you provided a lot more detail than in a much better explanation than I had, but it was excellent. It was just it's so strange, just for myself to, like I said, in the initial question, was just to kind of come across this idea of, oh well, I've been kind of basically working on an old operating system of how we understood the universe. It's for someone, at least where I thought that I had at least a good idea of how we conceive the universe, it was quite jarring, I guess, to come to that realization.
No, and that's great, and that's also very exciting. But I think if we're on the same page now, like even if you didn't have all the details that I gave, like this is I think the picture that most people have when they think of the Big Bang, is they think like, yeah,
Absolutely.
the universe is hotter and denser, it expanded to get the way it is today, so you can go all the way back where you extrapolate it back into a point, boom, that's the Big Bang. If I didn't know all the cosmology that I knew today, I would think the exact same thing. And in fact, this was what everyone thought once you accepted the Big Bang throughout the 60s and the 70s. There was just a few small problems with it. And when I say problems, I'm thinking about this from a scientist point of view, where I'm saying, okay, the ideal scientific theory is going to say, I'm going to tell you all the laws, and I'm going to start with some initial conditions, And then I can just apply the laws to my system and I can predict everything that's going to come out. If we do that for the Big Bang, you can ask, well, what conditions does it need to have? And there are a few things that need to be very specific. One of them is you have to have your universe be perfectly spatially flat. We have two sides of our equations to talk about the expanding universe. On one side is the actual rate of expansion, what we measure, that distance redshift relationship. On the other side is all the different forms of matter and energy present in the universe. Those two numbers, they don't have to match. But in order to get the universe we have today, that means at the very early stages of the universe, those two numbers needed to match to about 50 orders of magnitude. So that would be like you and me both taking an object the size of the sun, pulling out a dust mote's worth of matter, and seeing if you and I both picked the same amount of matter to be the mote of dust as each other out of the entire sun. That is about the same as your odds of winning the Powerball lottery with the numbers 1, 2, 3, 4, 5, 6, 5 times in a row. Sound like bad odds or sound like odds
Yeah.
you want to take?
I wouldn't take those odds.
Those are pretty lousy odds. We also have this puzzle that this leftover background of radiation that we found for the first time in the 1960s. It is the same everywhere we look, which means if you hold out your left hand and point and go 46 billion light years in that direction, you're seeing light with some very specific properties. And then if you hold out your right hand and you point in that direction and go 46 billion light years, you see light with the same properties that the light on your left hand side has. How is that possible if they haven't had time for a light signal to even go from that point on your left to your point on your right since the Big Bang? Somehow the universe knew it had to be born with the exact same properties, same temperature, same density everywhere, even though it doesn't have time to do it. That would be like looking at your room, which has a fireplace in the corner, and surprisingly find that your room is heating up evenly everywhere, even though the heater's in a corner. It's not the sort of thing you'd expect. So these are the kinds of puzzles that we had with the Big Bang. And there were a lot of people, and there are still some of them around today, who say, yeah, who cares? You have to start your system with some initial conditions, and these are the initial conditions you need to give the universe, and that's the answer, and let's have the Big Bang exactly the way we have it. I don't like that line of thought. To me, that's the line of thought of someone who has totally given up on the idea that science could solve this puzzle. Because what you do scientifically when you make a theory is you say, okay, we've got our old theory, we've got the Big Bang, and here are the things it explains. And we talked about them. It can explain the expanding universe. It can explain the formation of structure, like cosmological structure. It can explain the existence and properties of the leftover radiation from the Big Bang, known as the cosmic microwave background. It can explain the abundance of the light elements. This is all good stuff. But it also has those puzzles it couldn't explain. So a good scientific theory will do three things. Number one, it's going to reproduce all the successes of the pre-existing theory of the Big Bang. So everything the Big Bang can explain, if you want a new theory to supersede it, it has to explain all those things too. That first point, by the way, is why all of the Big Bang's alternatives fail. if you are on the internet, you can hardly go anywhere that talks about these questions that isn't full of people promoting these alternatives. Maybe it's the plasma universe or the electric universe or the steady state universe or the quasi steady state universe or a tired light universe, right? I could list off alternative explanations to the Big Bang all day. But you ask any of them, hey, can you explain the expanding universe, the cosmic microwave background, and the abundance of the light elements all together? No, none of them can do it. And that's why they're all, in the trash can to bona fide astrophysicists. But then you say, okay, is there a way to reproduce that? And there are actually a few ways to do it. But if you want to supersede the Big Bang, you need something that isn't going to just reproduce the Big Bang's successes. You need something that's going to succeed where the Big Bang didn't. You're going to need something that can explain why was the universe born at the Big Bang with these conditions? Why do the expansion rate and the energy density balance so perfectly? Why is the universe spatially flat? Why is it the same temperature in all these disconnected locations? Also, there are additional things. Why is the entropy in the very young universe so much lower than the entropy today? Why did there not form things like magnetic monopoles or these other exotic particles that have to come into play at some really high energies? If things got infinitely hot and infinitely energetic, surely you should have produced those things. So where are they? That's where the idea of cosmic inflation comes in, because what inflation says is before the Big Bang, where the universe is full of particles and radiation, maybe the universe was filled with energy inherent to the fabric of space itself. Maybe that's what the universe was full of. And if that's the case, your universe expands very differently. It expands like the fabric of space itself. Instead of expanding and cooling and having the expansion rate slow down, if all your energy is in the fabric of space, you don't have a temperature. Your temperature is zero. You have none of that stuff going on. So how do we decide if inflation is right? Because it's not enough to say, hey, this is really interesting. I figured out how to reproduce all the successes of the Big Bang, and I figured out a way to explain its initial conditions. You need to do both of these together. So for a while in the early 80s, there was a puzzle called the graceful exit problem, where people worked out, oh, here are some generic ways that you could go from an inflating universe and take that energy that's in the fabric of space and convert it into particles and radiation. So that's something we were able to do. But you have to go a step further in science. It's not enough to add a new thing, reproduce your old theory's successes, and also explain something new. What you have to do is extract new, novel predictions that have never been tested, that differ from the predictions of the pre-existing theory. So you need ways that inflation is different, that it predicts different things from the Big Bang theory. And guess what? When we worked those predictions out, mostly during the 80s, we were able to extract, over the next few decades, as our technology improves, we should start to see certain facts or certain factors that we can go out and measure. And those should be really cosmically interesting from our point of view. So what are those things that they're talking about? What are those things that you can go out and measure? Well, one of them should be, okay, we are going to have a perfectly uniform universe, except if inflation is right and quantum physics is right, then the energy in the fabric of space is going to be fluctuating because it's going to have quantum fluctuations superimposed on it. So that means we should predict the universe was very uniform, but on all scales cells, it's born with these tiny, tiny, less than a part in 10,000 imperfections. And those overdense regions are going to grow into stars and galaxies and clusters of galaxies, and the underdense regions will give up their matter. So when we make these predictions and we look at what happens, and then we look at the structure that forms in the universe, and we look at the imperfections in the leftover glow from the Big Bang, we can test, does it agree with inflation's predictions or not? We can test, is the universe almost perfectly spatially flat, but not quite, because there are those quantum fluctuations in the curvature of the universe. That's something that we can only test to a certain precision, and it's flat to the precision we can measure it. We haven't yet gone down to that next level of, do you expect these curvature imperfections to show up? You should be able to look at the original fluctuations that the universe was born with, and if inflation is right, these fluctuations should be at constant entropy with each other. There are a lot of things that could be constant. And there are other things that can change. If you want to expand something, you can expand it in general in two ways. You can expand it isothermally, which means you're keeping the temperature inside constant, but the entropy changes. Or you can expand it adiabatically, which means the entropy stays the same, but the temperature changes. So the universe should expand adiabatically and have these adiabatic fluctuations if inflation is right. And we've gone and measured them. And what we found is that at least 98.7% of the fluctuations are adiabatic, and no more than, this is an upper limit, 1.3% is isothermal. So that's a good verification of inflation. Inflation also predicts, I said that you should have these quantum fluctuations, but because of the physics of how inflation has to end and give rise to the Big Bang, we know that those fluctuations should be slightly larger magnitude, only by a few percent on the largest cosmic scales as opposed to the smallest cosmic scales. We define this by a parameter that we call the scalar spectral index. If all scales were equal, this parameter would equal 1. If the small scales had larger fluctuations, this parameter would be slightly greater than 1. And if, as inflation typically predicts, it has slightly larger fluctuations on the larger cosmic scales, the value of this parameter should be very slightly less than the number 1. We've gone out and measured it, and it's 0.965. So these are the types of things where I say this is everything you want from a scientific theory. This is a scientific theory that it reproduces all the successes of the Big Bang. It explains the things that the Big Bang can explain. And we've been able to extract 6 independent ways of testing cosmic inflation against a non-inflationary Big Bang. And of these 6 ways, 2 are not sufficiently tested. And of the 4 that are sufficiently tested to know which way they go, all 4 of them favor inflation and not the non-inflationary Big Bang. And that's the super short version. But even without getting all the details out of it, I hope that's something that you can follow and say, yeah, that sure does make sense.
No, absolutely, it does. It's you know, well, I guess we don't really need to get into it because I was going to ask, and I didn't really want to waste time on it, but I think a lot of people have a lot of people have a misconception about just the term theory, right? And where it'll get misconstrued as, well, it's a theory, it's not a fact, right? And I think that's a very common misconception from I would say the normie universe versus the scientific community.
Well, I mean, think about how we use it conventionally, right? You can say, like, I think the moon is made out of green cheese.
Yeah.
And you'll be like, well, that's just your theory. Or you'll be like, I think that vampires are the world's greatest golfers, but their curse is they can only play at night, so they can't compete. And you're like, oh, of course, that makes sense. But That's just a theory. In science, theory is not the same as wild guess. Theory is not the same as my idea. Theory is not even the same as my hypothesis. Um, a theory in science is like the highest thing you can aspire to. And when I say theory, I mean a robust, verified, validated theory. You can't ever prove a theory, but you can build up so much evidence for it that a theory is a theory that's reached the level of scientific consensus is more robust, more true than any single fact. Because any single fact can be overturned by one observation or one measurement. But a theory encompasses millions of experiments or measurements or observations that you can take or make. A theory is this overarching framework to describe how nature works, and it allows you to describe the phenomena you've already seen and make predictions for phenomena that have not yet come to pass. So you can say, oh, Einstein's relativity is just a theory. It absolutely is just a theory. It is possibly the best theory humanity has ever come up with because it is correct 100% of the time. It does not violate anything. Like nothing violates Einstein's relativity. Not general relativity that involves gravity, things that don't involve gravity, they don't violate special relativity. That is how all of this works.
Well, no, I appreciate that. I just it was just kind of nipping in the bud, maybe some listeners who may have a misconception about theory. And I did actually forget to ask you before we started how much time did you have? Because I mean, we're at about 50 minutes or so, and I had a lot more questions, but I didn't want to keep you any longer than you had available.
Well, I had planned on an hour, but
Okay.
if you want to go like 10 or 15
Okay.
minutes over, I can probably spare that. But if you have other questions, let's get to them and I'll keep my answers shorter cuz I gave you a really long explanation about the Big Bang and inflation and what this is all about cuz I think it's fascinating, and I think it's fascinating that geez, are you telling me that most people on earth don't know where our universe came from, even though the idea they have about this Big Bang and that's it is 40 years out of date? Like, I'm only 41, and I didn't hear about this until I was in grad school. So I'm not really a fan of how unsuccessfully this theory has been communicated to the general public, but that's why I wrote a book.
No, and I appreciate that. I'll keep it a bit succinct. So that one of the big things that I wanted to ask you about was, and I don't know how much in your wheelhouse this is, was kind of these keeping in context of the bigger kind of questions that we're asking is, the framework, I guess, of reality or the universe, however you want to phrase it, of there's these basically the conflicting theories are supersymmetry versus multiverse. And I remember watching some documentaries about when CERN was first coming online and confirming the Bogues hit what's it the gosh, now it escapes me.
Are you the Higgs
Yeah,
boson? Is
Higgs
that what you
boson
were asking
particle.
about?
And I remember that this is kind of me remembering back, but that they're saying if it was over a certain number, it was going to confirm one. If it was over this certain number, it was going to confirm the other. And basically, what I could uh, get out of it was that it was kind of in the middle or in between the two. There was no, or I guess it's a bad way to frame it, that there was no definitive answer in that. I know there's a bunch of other competing theories and sub theories within, supersymmetry and multiverse. But I was wondering if, just as a very kind of 30,000 foot view, if you were able to explain the concepts that they're talking about, and has there actually been any developments that I'm unaware of in kind of helping along to kind of sway one way or the other or towards any competing theory, perhaps?
Well, let's clear up what may be a small misconception. The multiverse and supersymmetry uh, are not things that are related to each other. They are both
Okay.
extensions to our standard picture of theoretical physics. But they're not competing with each other. They're not. It's either one or the other. It could be both, it could be one, it could be neither. The things we do at the LHC when we collide particles, when we see what comes out at various energies, and what certain particles that we make that are unstable decay into, we have this framework. We have this theory called the Standard Model. And just like relativity is our best theory to describe space time and motion through the universe, well, the Standard Model, which is it's like three quantum field theories all synthesized together to describe the nuclear interactions that particles make and the electromagnetic interactions that particles make with each other. Um, what you do when you make these measurements, you can see, how do these particles decay? What do they decay into? What are their masses? What are their spins? What is their opening angles between their decay products? How often does it behave this way versus that way? What about the antimatter version? How is that the same or different? You ask all these questions and you get some, values out of your experiment, and then you compare them with the predictions that the Standard Model makes. And everywhere we've made these predictions, we have found, oh man, at the LHC, we were really hoping we would see something that was a hint of something beyond the Standard Model, of something like maybe there's an extra particle out there. For example, if supersymmetry is right, there should be more than one Higgs boson. There should be probably five, but at least two. There should be at least two Higgs bosons. We've only found one, and we haven't found a hint, even indirect hints, of any others. If supersymmetry was correct, superparticles should exist, which is to say that there should be, for every particle like a quark or a lepton, there should be a superparticle partner that has a different spin but the same charge. We've looked exhaustively for these super partners, and we've pretty much constrained that if any of them exist, they are many, many times more massive than all of the Standard Model particles' masses combined. So we have some constraints, I would say, that disfavor supersymmetry and that don't tell us anything about the multiverse. But this is the limits of what we can do in the search for new particles. What I think is very interesting is the Higgs is the newest one. The Higgs is the newest particle. Almost all of the new experiments you can do, um, right? If you can write down, like, okay, if we add this new thing to the Standard Model to change it, how do we expect that to affect the Higgs results? They should affect what we call these decay ratios or the branching ratios or all of this at about the 0.1% level. And the LHC is really only good enough, even, pardon me, even all into the future where it takes its full suite of data, it can only get you about down to the 1% level. So if we really want to know if this Higgs boson is the Standard Model's Higgs boson, or if this is really an extended Standard Model and we have extra things that we haven't measured yet, the LHC is limited in what it can tell us like that about that. So this is, for me, one of the prime motivations for building a larger, more powerful particle collider, is that there are limits to what the LHC can teach us. And if it finds something new, that's really interesting. But if it doesn't find anything new, that doesn't mean that there isn't something new to find that's slightly beyond the machine's reach. As long as we have the capability to keep pushing those frontiers of knowledge, to keep finding what might be there beyond the currently explored frontier, we have to. This is not something that's going to cost more than civilization can afford. This isn't something that's even going to cost as much as it would cost to land humans on Mars. The cost to build a brand new particle accelerator and make it work and to have all these wonderful things come out of it, we're talking about the cost of a handful of fighter jets. So I don't know. If we think science is a valuable endeavor for humanity, don't we owe it to ourselves to push the fundamental frontiers as far as we can? When I think about all the technologies that have come out of quantum physics and relativity, who would have predicted that when we first devised these ideas? But almost everything we do, including the screen I'm looking at as I speak to you and the signals I'm sending to you over the internet, all of this relies on quantum physics and relativity. So I think if we want to know what those next breakthroughs, those breakthroughs that are coming decades or centuries in the future are going to be, these are the fundamental steps we need to take now to make it happen.
I completely agree. I think that we should once again reiterate our, and prioritize our I guess our sense of wonder at the universe and what's around us, and just as kind of one of the last, I mentioned earlier, where you wondered what was over that mountaintop, right? And so we've kind of conquered a lot of the more tangible physical questions, and can somebody climb to the top of that mountain? Can somebody get down to the South Pole and walk across it? Or even go to the bottom of the ocean, although that's largely unexplored as well. But I think it's one of the uh, I shouldn't say the last places of discovery, because the it's almost limitless, or I should say it's limitless definitely within 100 lifetimes of being able to understand all of this. And I agree. I think that it's so important for us to prioritize this sort of research, and discover what's where we are, and what uh, what makes up the world, or I should say the universe that we live in.
Yeah, and for me, what you just mentioned, that's one of the most exciting things about science. That's not a bug, that's a feature, is that when you reach the pinnacle of that mountaintop, you can see farther than anyone else has ever seen. And in addition, you can see the next mountaintop. You can see, oh no, I answered this question and it raised all these additional questions. That's a feature because science isn't going to end. We're never going to reach this place where we don't have more questions to answer. We might reach a place where it becomes impractical to probe what the answers might be, but we're not there yet. This is something where the will is there, the talent is there, the scientists are there, and the technology is there. So if we don't go for it, if we don't push those frontiers with next generation telescopes, with particle colliders, with finesse experiments that try to probe the little subtle hints of things we've seen that don't quite add up, like what the hell is going on with these weird massive little neutrinos? What is going on with some of these experiments like Dama or Libra that are giving puzzling results to in the dark matter sector? What about, right? And you can keep doing this for anything you find, it will raise more questions. And until we can no longer push those frontiers, I think we have to. I think that's part of what makes us human, is our curiosity, our sense of adventure, and our willingness to work hard to further our own body of knowledge.
And the very last question that I wanted to ask you was, what is going on right now that, and it may be, the subject, it's probably highly related to the subject of your book, but that you find, the most interesting, or that has you the most excited?
I mean, there's so much to be excited about. Whenever anyone asks me this, I'm always so tempted to say, Oh man, I got to pick one of these big existential puzzles of our time, right? Like what is dark matter? We have all this indirect evidence that dark matter exists, but all of our attempts to directly detect whatever particle might be responsible for it has come up empty. So is there a particle that's just out of our reach? Is there a particle that only interacts gravitationally and doesn't have any standard model interactions? Is it something else entirely, like a dark fluid that would never show up in a particle detector? That's a puzzle. I could talk about the dark energy puzzle. Why is the universe expanding at this weird accelerating rate it seems to be expanding at? Or I could talk to you about the baryogenesis puzzle, which is, look, we're made out of matter and not antimatter, and all the stars and galaxies are made out of matter and not antimatter. But if we look at the leftover glow from the Big Bang and say, hey, how many photons are there for every proton in the universe? The answer is more than a billion. There are more than 1 billion quanta of light for every proton in the universe. So, why did matter win out over antimatter? But also, why did it win only by this small amount? That's a big question, too. So, we have all of these big existential questions, and I could list more and more and more, but we're going to run out of time. So, what should we do about that? Should I pick one of those questions as the big thing that drives me? Or should I think about it in a different way? And the different way would be to say, okay, let's take a look at the limits of our current tools, of our current instruments for a particle collider. How energetic can it get, and how many collisions can I get so I can see what comes out? For an astronomer, that's something like, how big is my telescope mirror? What wavelengths can I observe in? How much noise is there that I have to filter out? What types of instruments do I have hooked up to it? If we want to know what lies behind the next frontier, we should be asking, what can I build to test the universe in ways it hasn't been tested before? That's the sort of thing I'm most excited about. Not, when I think of like the James Webb Space Telescope, which is launching pretty soon now at last, right? We're barely a year away from it. Um, yeah, the James Webb Space Telescope, it's going to try to capture images and data about the very first stars ever to form in the universe, something that's even beyond the reach of Hubble. We're going to try and find things like pristine gas left over from the Big Bang. We're going to try and find galaxies that are in the process of growing up, the first galaxies where these early star clusters merge together for the first time. I could be very excited about all of those things. But wow, if I had tried to do that for Hubble, I wouldn't have predicted Hubble's biggest discovery, which is that the expansion of the universe is accelerating and therefore dark energy must exist. That wasn't the goal of Hubble. The science goal of Hubble was to measure the Hubble expansion rate of the universe. And it did. It found it was 72 plus or minus 10%. And now, today, 2019, we have a controversy because one technique for measuring the universe, or I should say a set of techniques, says, yeah, we didn't get 72, we got like 67, which is totally consistent. But there's another set of groups using a different set of methods, and they say actually it's 74, which is also consistent with 72. The thing is, the 67 and the 74 aren't consistent with each other, and that's a real puzzle. So I don't know what to say, like, oh, that's the puzzle we should be investigating, as much as I know how to say, here are the things we know how to build. Here are the things that we know how we're pushing these frontiers. I don't know what the payoff is going to be, but I fully expect there's going to be a payoff.
Well, I'd really like to thank you for coming on the show today. How can people find you and consume your content?
Well, if you want to find me, I'm best known as Starts with a Bang. I am Starts with a Bang on Twitter, Tumblr. My blog, which airs new articles 6 days a week, is on Forbes at forbes.com/sites, sites/starts with a bang. Or if you really want to make my day, you can support me on Patreon. The Starts with a Bang has a Patreon at patreon.com/starts with a bang, and it's supporters that keep me going and keep me able to keep doing what I'm doing. And I'm just thankful that I can make a living sharing what I know and what we know as a species about the universe with everyone out there who's curious to learn about it.
Well, you do an excellent job conveying all this information, and I will have links to all this, the blog, Twitter, Tumblr, everything like that at digiknowcrypto.com/EP56 for episode 56. And Ethan, thanks again.
My pleasure. Thank you, Dustin, for having me on.